looking at this equation where we substitute F over m for the acceleration in the kinematic equation for Vf squared, we can solve this equation for F delta S. Now remember when we posed the question a few days ago, or a few lectures ago, about an object accelerating the same distance down an incline, but starting at different velocities, coasting the same distance down the same incline, starting at different velocities. We noted that the F delta S was the same in every case, but the change in velocity was different because the acceleration was always the same. With a higher velocity, we had less time to accelerate. So there was less change in velocity, but you remember that F delta S was going to be proportional to the change in the squared velocity. We can take that idea just a little further here. If we solve for this F delta S here, and I haven't gone through the details of it, but if we solve for F delta S, and we do that simply by subtracting V naught squared from both sides and multiplying by the reciprocal of 2 over m, which will be m over 2, that gives us an m over 2, or 1/2 m Vf squared minus 1/2 m V naught squared. And that's what our F delta S is. Okay, now, this F delta S is the product of the force exerted and the distance through which it is exerted. Okay, we call this work. So this F delta S we're going to call work. And this 1/2 mv squared we're going to call kinetic energy. And we're going to think of the situation as follows. In order to accelerate an object from a velocity v naught to a velocity vf, an object of mass m, we're going to have to do a certain amount of work, a certain F delta S. Okay, so work is force multiplied by the displacement through which we apply the force. Now there's some caveats here. The force has to be parallel to the displacement and so forth. You'll read about those in your text, and I'm kind of glossing over those things, but we're trying to get the main idea here. Okay, F in this situation is the net accelerating force. It's not necessarily the force we apply. If we apply a force and friction resists us, then the net force will be less than what we apply. It's the actual effective force. It's actually the sum of all the forces. My force plus the frictional force. If there's some air resistance, we've got to take that into consideration. Some of those forces fight each other. So when we add them, we end up with less than we started. Okay? The net accelerating force, for example, when we did the cart on the incline, we had the F delta S of the washers minus the friction. The force of the washers minus the friction, that was exerted through some delta S. As the washers declined, gravity allowed that situation to do work, allowed the washers to do work on the system. When we write this equation, F delta S equals 1/2 m Vf squared minus 1/2 m V naught squared, this is then the change in kinetic energy. If 1/2 mv squared is what we call kinetic energy, then this is the final kinetic energy minus the initial kinetic energy, or the change in kinetic energy. And we see then that this equation tells us that the work of the net force equals the change in the kinetic energy in this situation.